Welcome to This Explainer. Today, we're diving straight into some cutting-edge research from the 8th Annual Learning for Dynamics and Control Conference, or L40C for short. We're going to explore exactly how modern robots are learning to navigate our completely chaotic world. For the longest time, robotics was kind of stuck inside these highly controlled factory floors, right? Well, those walls are coming down. Let's unpack the science of how robots actually learn physical tasks.
Okay, so here's the core problem. Programming a virtual robot arm to move from point A to point B on a screen, that's one thing. But how do we teach it to handle the messy, unpredictable physics of the real world? Friction changes, objects slip out of grasp, a gust of wind blows. Actually touching the real world requires a completely different kind of artificial brain.
To figure this out, we're going to break down the anatomy of a learning robot's brain into 5 quick parts: the physical learning challenge, mapping the chaotic world, mastering movement and contact, building in safety guarantees, and finally, the AI robotics frontier. Let's get into it. All right, part 1, the physical learning challenge. Now think about this number for a second, 331. Volume 331 of the Proceedings of Machine Learning Research is just massive. It represents a global collaboration containing over 80 wildly complex research papers, all completely dedicated to solving robotic physical interaction and dynamic control. The brightest minds on the planet are dedicating their entire careers just to figure out how a machine can pick up a slippery glass of water without shattering it. To really grasp this research, we need to define the core theme of the whole conference: dynamics and control. Essentially, it's the science of predicting the future. It's the mathematical framework we use to model how physical systems change over time, which lets us influence them to do exactly what we want. It is literally the absolute bedrock of physical learning. Which brings us right into part 2, mapping the chaotic world. We're seeing a huge paradigm shift right now. We are finally moving away from those rigid, pre-programmed robots where every single tiny movement is hard-coded by a human. The kind that just completely panic if a chair is moved 2 inches. Instead, we're moving toward adaptive, learning-based dynamics, where robots use real-time data to survive and function in totally unscripted environments. And to pull this off, researchers are building immensely complex mathematical models. Papers like DPNIP are predicting environment dynamics, while Cable Robot GraphSim uses graph neural networks just to model floppy, partially observable cables, which, by the way, is a total nightmare for a robot to understand. Then there's ECO, handling energy-constrained operators. Scientists are basically inventing entirely new math just so a robot can predict what's going to happen next in a messy room. Okay, moving on to part 3, mastering movement and contact. So once it understands the room, it has to move. Look at the Falcon system. It stands for Force Adaptive Humanoid Locomanipulation. It doesn't just step blindly and hope for the best. It constantly senses environmental forces. When it makes contact with the ground, it adapts dynamically in real time before executing its next move. It's literally feeling its way through the physics of the environment to learn how to walk and grab things. Because for robots, touch is absolutely everything. Researchers Shafif Omar and Majid Khadiv frame mastering physical contact not just as some isolated skill, but as a unified requirement for multitask learning. Basically, if a robot can't understand contact, it can't do anything out here. Mastering touch is the master key to unlocking a robot's ability to perform everyday tasks. To get that fluid movement, teams are deploying some seriously advanced concepts. Take Halo, hybrid auto-encoded locomotion. It uses things like learned latent dynamics and Pointgarry maps. And hey, you don't need a PhD in math to get why this matters. These tools make sure robots don't just blindly trudge forward. They move with calculated balance, anticipating their center of gravity shifting before it even happens. It's a real game changer. But an adaptive robot moving freely is super dangerous if it isn't safe. Which leads us to part 4, building in safety guarantees. You might be surprised to hear that a massive portion of robotics research isn't about making robots faster or stronger at all. It's entirely focused on creating mathematical safety nets. Frameworks like control barrier functions and safe exploration are specifically designed to stop a learning machine from destroying itself or injuring us when it inevitably gets confused or hits a random delay. I absolutely love this paper title, How to Train Your Latent Control Barrier Function. Aside from being an amazing movie pun, it hits the engineering goal perfectly. They're building a smooth safety filter. Think of it as an intelligent, instant override switch. If the robot hits a physical constraint it's never seen, like a door slamming shut, this filter smoothly takes over to ensure total safety without crashing the whole system. All right, let's look at the really futuristic stuff in part 5,
the AI robotics frontier. The absolute bleeding edge at L40C right now is merging these physical dynamics with modern generative AI. Through projects like Cofine LLM, scientists are conformal fine-tuning large language models specifically for language-instructed robot planning. This means you can use natural, everyday speech to give a robot an instruction, and the LLM translates your words into the complex physical planning needed to execute the task safely.
This is exactly where the field is heading. Robots aren't just reading text anymore. They're using vision language models to control complex musculoskeletal movements. Even crazier, they're taking language guidance to update their probabilistic safety certificates on the fly. You can literally tell a robot, hey, be careful that mug is hot, and its internal safety math updates instantly.
So all these incredibly complex mathematical and engineering pieces are finally snapping together. And as we transition from static code to dynamic, learning machines, it leaves us with one really provocative thought. When these autonomous machines finally learn to safely touch, see, and navigate our chaotic physical world using the power of language models, how will their presence reshape our everyday human spaces? It's a future arriving way faster than we think. Thanks for joining me on this explainer, and keep exploring.